afternoon. This afternoon I'm going to be talking to you about validating the quality of your mirror. I'm going to assume, for the purposes of this talk, that you already are familiar with the focal knife edge test and the modification of it using a raunchy screen instead of a knife edge. I'm also going to assume that you know how to measure the zones on your mirror against the knife edge position, where the knife edge relationship to the zonal radius is h squared over r, where r or h is the zonal radius and r is the center of curvature, and that you know how to take those measurements to test your mirror, and you have a table of numbers, and now we're looking to establish the quality of your mirror. So in this presentation, what I'm going to do is talk about what are the standards for a good mirror. The most common one, the one most talked about, and I see most frequently in advertisements, is the quarter wave standard. It's not the only one, but we're going to examine that just a little bit and put that in perspective, we hope. And then I'm going to discuss the three most common ways that are available to amateurs. These are the ways written up in most textbooks on how to achieve the standard. And we'll spend a little bit of time talking about what's realistic to achieve, and I'll try and show you a sample mirror in the process. First, talking about established standards. First, a little physics, just so that we're on the same page here. Ideally, if we lived in a real world, we would like an optical system that could take a point of light that is infinite distance away and has no size, and after it comes through the system, have it focus to a point of light with no size. Unfortunately, we don't live in an ideal world. Light is a wave, and light is subject to some of the properties of waves. One of them is diffraction. So when light travels through an opening, like a slit or a circular aperture, or goes around a corner, then the light that goes right at the edge of the corner, there's some destructive and constructive interference going on, so that the light coming through the system is no longer going to be a point of no size. It's going to be a point spread function. And that point spread function is going to include a central disk, which has by far most of the light in it. But that central disk is a finite size, and it's going to be surrounded by a series of rings, the first two or three of which you may see. This disk is a very predictable size, a very predictable radius to it, and that's a function of the diameter of the aperture. The disk is also called the Airy disk after the physicist who did the work to name it. So we know that a telescope can never be so perfect that it's going to focus a piece of light that has no size into a point that has no size. It has to focus it into this point spread function pattern. And our optics are good, or we consider they're good, if they get close enough to this pattern that we get all the resolution out of the telescope that we hope to get. You can think of that Airy disk as a pixel. Now that we're all computer literate and we know what images made of pixels are like. It so happens that the light that's in that Airy disk is 84% of all of the light that comes in is going to be in that disk, and the remaining 16% is going to be scattered throughout the rings. That's, mathematically speaking, for a totally perfect system. We would like our telescope to get as close to that as we possibly can. But as we're going to see, deviations or errors in our telescope, especially correction for spherical aberration, is going to deviate from those percentages. This graph here is just a profile showing the point spread function, and it's showing even that the Airy disk itself is, there's a ramp up as it goes up to a maximum peak intensity and down, and then you've got the rings on either side of it. The two most common criteria that are used for us to judge our mirrors against is the Rayleigh criteria, more commonly known as the Rayleigh quarter wave criteria, and the Danjon and Coder criteria. Now these are two separate criteria. They say different things and they mean different things. There is overlap. If you make a mirror satisfying either one of those criteria, you're going to have a mirror that you're going to be darn proud of, but they aren't the same criteria. So let's discuss the two criteria. What are they? What do they say and what do they mean? first one, the Raleigh criteria, says, or at least these are the words you're apt to see written up in the optics books and optics articles and so on. You're going to see words similar to this. If light coming to a focus has no optical path difference error exceeding a quarter the wavelength of light, the optical system will be sensibly perfect. First, let's say that's probably not exactly what Raleigh said. I'm doing a little research on it, I want to do some more, but some tidbits that I have found so far are more like a quarter wave of primary spherical aberration will result in 20% reduction in the luminance at the Gaussian function. So really, if you get close to Raleigh's words, you get the indication already that at a quarter wave we do have a reduction in the central the light in the central airy disk, and you're just at the threshold of beginning to notice it. That still makes it a good criteria, but let's just be clear about what it says. What do we mean by optical path difference exceeding a quarter wave? Well, let's just try a little visualization here. You have light rays traveling here left to right, and it consists of pulses of photons going forward connected by fronts, and the front is generally considered perpendicular to the light ray. If you have light rays converging into a focus, then the wave fronts are going to be spherical shells converging as the light rays are conical. So imagine two spherical shells converging to a focus that are 1/4 wave apart. Then what the intent of the Raleigh criteria is that your spherical aberration, if the correction for spherical aberration deviates by 1/4 of a wave, and here we have the edge rays leading the center rays by 1/4 of a wave, so that's optical path difference edge to center. This is just at the margin of the Raleigh criteria. You will probably lose about 20% of light in your luminance, and that is a judgment that that is just at the threshold when you start to notice some deterioration. Now this is also can be thought of as what we call peak to valley, high peak and low valley. So the peak to valley is 1/4 wave, and these are wave fronts. What it was showing here is the undercorrected condition. It's also true for the overcorrected condition, where the edge rays are lagging the center rays by 1/4 of a wave. Both of those conditions are at the limit of the Raleigh quarter wave criteria as we understand them. Remember, this is peak to valley at the wave front. The reason I want to point that out is because when we're dealing with mirrors and reflecting surfaces, any light ray that hits a mirror and bounces back, there's an equal angle reflection, so that the surface accuracy has to be half what the wavefront accuracy is. So if your wavefront, you're looking for quarter wave, the surface accuracy has to be 1/8 of a wave. But all in the measurements and the reduction that we do deals with wavefront. But just keep in mind also, so that if someone starts talking that they've got 1/8 of a wave mirror or something, you might need to clarify whether they're talking surface accuracy or wavefront accuracy, because all these criteria apply to wavefront. I want to point out that the Raleigh criteria is not intended to mean that anything goes between those two quarter wave shells. Whether or not the light from the front is going to hit the target, which is the airy disk, is more a function of the angle. And if you have too many lumps and bumps in the wave, then you can have angles that are more than what's anticipated, sending the light out of the center of the airy disk. Now that's the Raleigh criteria. The other criteria was created by André Danjon and André Coder, both French, both worked at the Observatory of Paris, and they have two elements to their criteria. The first one, or two conditions, the first condition states the geometric image of least confusion in the plane of focus should not exceed the size of the theoretical airy disk. And the second one is the maximum wavefront error must not exceed 1/4 of a wavelength of light, and the defects should be much less than this over most of the surface. This second condition here, that's the first time we really start seeing words that suggest that the error differences can be local as long as they're within a quarter of a wave. But we've got two conditions to this criteria, and that is that the geometric image of least confusion in the plane of focus must not exceed the size of the theoretical area disk. So what is the circle of least confusion, and what do we mean by this criteria? Consider we have an optical system, and it's focusing light coming in from infinity, and it has spherical aberration because it's a spherical surface. The edge rays are going to focus closer than the center rays. They're going to focus farther away. And now I'm going to blow up this area here and take a close-up look. And we can see that where the edge rays focus and where the center rays focus, this line here is the longitudinal aberration. And somewhere in between there, all of our light rays are going to come to a thinnest point. And that is called the circle of least confusion. Now, as we take our spherical mirror and gradually bring it through its series of ellipses toward the parabola, this longitudinal aberration is going to get shorter, the circle of least confusion is going to get smaller, and when we reach the point where the circle of least confusion is smaller than the area disk, then we're going to have a telescope that's about as good as we need to get it. This is where the term diffraction limited comes from, because the light is all, according to the mathematics and according to the ray trace, all the light is going to go into the area disk. Now there can be some dispute about that, but at this point all I want to say is that this is commonly what's meant by diffraction limited. Now let's take just a look at and put into perspective the quarter wave standard, because that seems to be the one most people think about and talk about, partly because it includes a number, quarter wave, which means we can be better than that. 1/8 of a wave, 1/10 of a wave, 20th of a wave, 30th of a wave. How far do we have to go? This is a table. It's a table that I see in many places, but I happened to get it from a manual for telescope makers by Karen and Jean-Marc Leclerc on page 70. This is a recent publication from Wilman Bell, and this table shows the amount of light that's in the area disk for perfect optics as well as various imperfections. We can see, as I've already told you, perfect optics, 84% of the light is in the area disk. The remaining 16% is scattered into the rings. When you get 1/16th of a wave, you're down to 83%. When you get 1/8 of a wave, 80%. Now notice, from 1/8 to a thick 1/16th, all your 20th of a wave, 30th of a wave, 50th of a wave, it's all scattered between 80, 83, and 84%. It takes getting down to a quarter of a wave before you start getting a big jump, where now at quarter wave, primary spherical aberration difference, you get 68% light in the area disk and the remainder in the rings. And at a half wave, 40% is in the area disk and 60% in the rings. So you've got more light in the rings than you do in the area disk. So I just took the opportunity to plot that for you, to try to give you a little visualization. In this chart, wave rating is along the x-axis, and light in the area disk is along the y-axis. You're starting with a half wave, and then quarter wave, 1/8 of a wave. So smaller wave ratings come toward the 0, and increasing light in the area disk goes up. And you can see that the line between half a wave, quarter of a wave, and 1/8 of a wave is pretty steep and reasonably linear. But as soon as you get to 1/8 of a wave, then this curve starts to bend over, and you then start getting into what's called the area of diminishing returns. In other words, you don't get very much for an increasing improvement beyond 1/8 of a wave. So let's take a look at a couple of points here. We've got the Rayleigh limit at a quarter of a wave. And if you need to get a little calibrated on that, keep in mind that every Schmidt-Cast telescope out there has got a central obstruction that's 33%. That means, because of that central obstruction, that telescope system is quarter wave, at best. If the optics are absolutely perfect, beyond reproach, it's a quarter wave system. And yet, when you look at your Sky and Telescope gallery pictures, your astronomy magazine pictures, and everywhere else, all the websites where you go and you see these fantastic pictures of Saturn and Jupiter and Mars at opposition, and all of these highly detailed photos taken with these Schmidt-Casts, they're all quarter wave systems. No better. Nothing better. Can't be. So really, a quarter wave does give you a very good telescope. But it has been argued, and probably legitimately so, that under ideal seeing conditions, a very experienced observer looking at two telescopes side by side might notice a little softness of the quarter wave telescope system. And so let's crawl up the curve to 1/8 of a wave. Let's go beyond that to a 1/16th of a wave. 1/16th of a wave is known as the Fresnel limit. He did some work and wrote up that as far as he could see, and as far as he could tell from all the experiments he conducted and all the mathematical work and physics work he did, that once you get to a 1/16th of a wave of primary spherical aberration error, that 83% of the light is in the airy disk and it's virtually indistinguishable from 84%. That further figuring of a mirror beyond that point is absolutely, you're wasting your time. You're never, ever going to see it. I'm just going to zero in now on that particular section of the curve. Here's an 1/8 of a wave. Here's a 1/10 of a wave. A 1/10 of a wave is 81.6% of light is in the central airy disk versus the Fresnel limit, which is 83%. And I'm telling you, I would want anyone in this room to stand up and be counted if they think they can tell the difference between 81.6% light in the airy disk and 83%. So really what it boils down to is when it comes to wave rating for a mirror, assuming that we're talking a smooth surface and only talking primary spherical aberration error, that a quarter wave mirror is really quite an acceptable standard. If you're making a first mirror and you get it to within a quarter of a wave, you're doing very good. And the 1/10 of a wave is the most you ever really need to consider. Really, anyone who claims beyond a 1/10 of a wave, the measurement of that gets a little problematic, and I'd be a little skeptical of how reliable it is to say that it's a 20th of a wave or something like that. Keep in mind that what I'm talking about is complete systems here. Naturally, if you have a mirror that's going to be in a Newtonian, you're going to have a secondary. If it's a reasonably long focus, the secondary is going to be small enough. You're going to introduce some additional aberration. You probably do want to get your mirror itself a little better than a quarter. But the point is, these are the kind of ranges, these are the kind of numbers and wave ratings that we're talking about. And I wanted to point this out because I want you to make mirrors. I don't want you to beat yourself up taking some mirror in a basement and slaving over it for 3 years trying to go for a 20th of a wave mirror. It just isn't there. Just, if you want a good one, make sure it's better than a 1/10. But if you get anything between a quarter and a 1/10, and you mount it properly in the tube, and you have good collimation and a good secondary, and you've done a good job with your spider design in your tube, you're going to have a telescope that's going to give you just incredible performance, and you're going to enjoy it for astronomy. And let's not forget, that's what we're doing. We're making telescopes for astronomy. So, okay, that's nice. How do we satisfy these criteria? I'm going to be discussing 3 basic areas. First, I'm going to try to describe the classic method. This is for either people just getting started or people who really don't want to get involved in the real mathematics, the real optical mathematics, but they do want to make a good mirror. They want a simple criteria for where can their knife edges be, what are the boundaries for their knife edges. I'm going to describe Texereau's method. Texereau, he wrote his book, How to Make a Telescope, in 1951, and it was later in French, and it was later translated into English here, and it is essentially the standard. Most methods that come up with a way of judging amateur mirrors based on knife edge readings in some way use Texereau's methodology. Then I want to talk about the Mills-LaCroix method. That's an article they wrote in Sky and Telescope in the 70s, and they really took Texereau's method one step further and made things a lot simpler, a lot nicer. So we're going to really discuss these 3 here, and maybe a few other methods, but these are the ones that you'll hear the most about. This first method, what I'll call the classical method, was first described by Frank Wright in a Scientific American magazine, later published as ATM1. His article came out in 1933. This methodology then was carried on by Alan Thompson when he wrote his book, and Neil Howard and Sam Brown. They used this in some form. So we're going to describe it a little bit, and I hope I don't take too long describing it. I want to say right up front, this method starts with a scientific thought, but then it deviates from the science and goes to experience. The science isn't complete, but it's complete enough to get you partway there, and then they could say, but we know from experience if we use this tolerance, you're going to get a good mirror. And a lot of mirrors have been made this way. The simple part of the thought, and the reason this is so good, like I say, you don't need a degree in nuclear physics to figure this one out. You start with a spherical mirror. which you know is undercorrected, and you want to push it to a parabola. You want to have the sides go out so the marginal rays focus where the center rays do. If you have a parabola and a sphere that touch at the center, you can calculate what the difference in the material would be. And that relationship, the difference between the parabola and the sphere, is y to the 4th power divided by 8 times the radius of curvature cubed. So you only need to really solve this once. You really need to solve that at the edge of the mirror. So if you consider an 8-inch f7 mirror, the radius of the mirror is 4 inches, radius of curvature is 112 inches, so you solve for d and you get 22 millionths. That's the difference in class between the sphere and the ideal parabola. You also know from your r squared over r formula what the knife edge movement has to be to go from a null at the 0 to a null at the edge for a parabola. So whatever that r squared over r travel is, it's going to result in 22 millionths worth of difference between the parabola and the sphere. Just so happens that 22 millionths is the wavelength of light. But don't let that confuse you. It just happens to be a factor in this particular example. However, what we do know, since it is the wavelength of light, that a quarter of a wavelength of light is 5.5 millionths. We can take this sphere and push it out to a parabola. We don't have to push it the full 22 millionths. We only need to push it 3/4 of the way. Or we need to go 22 millionths plus or minus 5.5 millionths. And 5.5 millionths happens to be 25% of 22 millionths. So you need to go your r squared over r value plus or minus 25% in this example. Now, I want to emphasize, we're starting with a sphere. This is a knife edge cutoff of a sphere at the center of curvature. There are no zones, there are no holes in the center, there are no hills in the center, there are no turned edges, there are no bumps, there's no dog biscuit or rough surface. This is smooth, even, flat cutoff. And if I use my raunchy lines, they're straight, parallel, even, evenly spaced, edge to edge. So we're starting with that. We're not starting with something that looks like this. And then you're taking your smooth sphere, you're pushing it out to a parabola, and when you look at your parabola, you can tell that you've got a nice smooth transition from the center to the edge. This nice smooth blood cell looking appearance, and we've got a diffraction ring around the edge, meaning that the edge of our mirror is good. This is just a stamp in the center so I can do collimation in this particular mirror. So knowing that and giving that, we're going from full correction to be 22 million, so we need to go plus or minus 25%. So this kind of goes down to that, and I'm just going to come down here and say the r squared over r for an 8-inch f7 mirror at the 95% zone, where the radius is 3.8, is 0.1289. So my tolerance around that knife edge position, null out the 0 zone, and you move your knife edge back to 0.1289 plus or minus 25%. So my tolerance around that is 0.097 to 0.161. And then I prorate all my other zones that way. All you have to do is just come up with 3 or 4 zones. If it's a long focal ratio mirror, 3 or 4 zones is plenty, because you can qualitatively tell by looking at it that it's smooth. So you've got your 95% zone, your 70% zone, your center zone, and something in the middle. You calculate what your r squared over r is supposed to be. That's what your ideal knife edge position should be. And then you have a r squared over r minus 25% for each one of those, and an r squared over r plus 25% for each one of those. And you end up with a min and a max tolerance. If you graph that min and the max tolerance, it's going to look like this. Now, we have since learned that this isn't really what the boundary curve is supposed to look like if we follow true optics. It's not supposed to converge at the center. But by making one that does converge at the center, this is where they could say, experience says we can stay with a surface at a quarter of a wave rather than having to deal with it. We end up with something a little wider than you might think at the top, but it does work. And I'll show you that toward the end of the presentation here. This is Howard's mirror, how it happened to fit within the tolerance, and I would just like to again emphasize that It's better if you can keep all of your points so that you are a nice curve, but you're just one side or the other of your ideal line, but staying within the boundaries, you're going to have one heck of a mirror. And the closer you get to your true r squared over r, the better it's going to be. This isn't all that good for anywhere between the boundaries criteria. So method works best for focal ratios that are relatively long. It will work for shorter ones, but it's harder to tell that it's smooth. Your surface has got to be smooth, continuous, undercorrected ellipse, overcorrected hyperbola, and it's not well suited for fit between the lines criteria. So that's really about all I want to say about that. You're not going to get a wave rating out of it, but you are going to get a good mirror without having to know all the rocket science that goes along with it. Now I'm going to talk about Texero's method. Again, this one forms the foundation for everything that follows. And it's a little bit intimidating, and a lot of people kind of read the book and shake their head and don't know how to understand it. So I want to walk through it a little bit. And I also want to point out that if you have access to Amateur Telescope Making Magazine, issue 32, Dick Suter wrote a real nice article called Testing Paraboloidal Mirrors. And in it, he takes a section of that article and helps you walk through Texero's method. Texero's method does not establish a plus or minus tolerance for your knife edge reading. What Texero's method does is based on satisfying the Danjon and Coder criteria. The D&C criteria has two elements, remember, and Texero has outputs in his reduction methods for both criteria, the condition 1 and the condition 2. Let me start with a couple of terms, because the first thing he has you do is make a coder mask so you can measure your zones. And the HM is the center of your zone, and the HX is the outer edge of your zone. Those terms appear in his data reduction sheet and his other analysis, so I just want to start out by defining that this is how Texero defines his zone. HM is the center. That would be your small r, if you want to do small r squared over r type thing. Then he goes to this particular chart. This one here can be a little intimidating because it's kind of busy. So let's take a moment and go through it step by step. Because what we're going to do is use this analysis to satisfy condition 1, which says that the circle of least confusion is going to stay inside the Airy disk. So I've cleared all of the stuff away and only left the first part of this diagram. I've got two wavefronts. I have a dotted line wavefront, which represents an ideal wavefront. And I have the solid one, which represents a wavefront that's affected by a zone in a mirror. Now, these wavefronts are just a molecule away. They have just reflected off the mirror. They're a molecule away, so they are still the focal length f away from where they're going to come to a focus at point P. That point P is the ideal focus. That's what I want. That's where my r squared over r would tell me my knife edge should be for that radius. But I have a zone here, and I have an anomaly, and therefore the wavefront has an anomaly, and therefore the light is not going to focus at P, it's going to focus here. Now, I just want to say again, this analysis, I'm taking parallel rays coming in, I'm analyzing the optic as it's being used in a telescope, and these are points at focus, not center of curvature. So anyway, my aberrant ray is not going to focus at point P, it's going to focus at some little distance away. I'm going to call that distance a longitudinal residual aberration, capital delta F. That's the difference between what I want and what I got at the focus. At the focus. We don't measure at the focus, but this analysis so far is at the focus. I have to translate from the focus to the center of curvature where I do my measurement. But I'm not there yet. I'm going to get there. The next thing is, since this aberrant ray is focusing long, at the focus, it's a blur circle. And at blur circle has a radius small lambda f. Ha! You see where I'm going, huh? I want to make sure that this small lambda f is smaller than the radius of the Airy disk. So at this point, I'm just going to use some fairly simple trigonometry because I can't really measure that directly, but I need to find the relationship of that with respect to terms that I can measure. So just a simple trigonometric exercise using similar triangles helps to solve that. I know that with similar triangles, h over f is equal to little lambda over big lambda f. Okay, these are similar triangles because they have the same hypotenuse and so on. So I can have transverse aberration, little lambda f, over my longitudinal residual f is equal to h over f. This is a number I know. It's the radius of my zone. F is the focal length. I know that. That's the number I want. This is a number, I can't really measure this one, but I can in turn make that one come into terms with something I can measure. So, we know that that residual longitudinal aberration, lambda f, I can't measure, but I'm going to be measuring at the center of curvature. What do we know about the center of curvature? The center of curvature is twice the radius. Any error at the center of curvature is going to be twice any error at the focus. This entire analysis is written for a stationary light source and a moving knife edge. When you have a stationary light and a moving knife edge, you add another factor of 2 to your readings. Because ideally, you'd like your knife edge and your light source to travel together for everything to be really right. So my residual aberration at the focus is equal to the residual aberration that I can measure at the center of curvature divided by 4. Factor of 2 because I'm going from focus to center of curvature, and factor of 2 because I have a stationary light source and a moving knife edge. So that's where that factor of 4 comes from. So going back to this similar triangle exercise, first thing is, this is what I want to solve for. I want to solve for this transverse aberration because I want to test to see if that's inside the airy disk. So I take this term and put it over on the other side of the equation, and I know that this capital lambda f is equal to the residual at the center of curvature divided by 4, so I'm going to make that substitution, and I come up with my transverse aberration equals my residual lateral aberration at the center of curvature, which is something I can measure, times h, which is the radius of the zone, which I can measure, divided by 4 times the focal length, which is something I can measure. Good! I now have things I can measure, and therefore I can calculate what this transverse aberration ought to be. And I can compare it to my airy disk. Wonderful! Isn't that simple? Pretty clever, I think. Now, as far as data reduction, one of the things Texero does is this becomes a term by itself. For every zone, he'll calculate an h over 4f and put it in his table. That way, once he gets his residual, he can then just take that residual and multiply this, which has already been done, and come up with his transverse aberration. And that's why there's a row in his spreadsheet for hm over 4f, and then a row in his spreadsheet for this, and then you multiply those two rows together to get this. So I found my transverse aberration. I'm going to be able to compare it to my airy disk. That way I'm going to be able to satisfy the Danjon encoder condition 1. The condition number 2, I have to do some work to come up with a wavefront analysis. And that is essentially understanding the slope, the difference in slope between the ideal wavefront and your wavefront. That angle, that change in slope, happens to be the same as this angle here, which can be described as lambda f over the focal length. So you can come up with this slope angle is equal to this transverse aberration divided by the focal length. So we have all the elements we need now to understand what Texero does. This is a page out of his book. This is his table, his data worksheet, which looks a little intimidating. This box here is his first output. This is where he plots his transverse aberration compared to the airy disk, and this is where he does a wavefront analysis. So this satisfies condition 1, this satisfies DNC condition 2. So just really quickly going through this, because now that we have Excel spreadsheets, you can do this whole thing in an Excel spreadsheet. What I did when I did it is I had 13 columns and 4 rows rather than 4 columns and 13 rows. I usually like to do my arithmetic up and down horizontally, and I can use the graphing function a little bit easier that way. But anyway, the first 9 columns are pretty much boilerplate, and the working columns are 10, 11, 12, and 13. So here, hx, that's the outside border of your zone. That's your number from your encoder mask. hm is the center of your zone. hm squared over r. These are your ideal knife edge positions. The hm over 4f, this is that factor that I just told you about that you're going to be multiplying your residual by. We make a table of it, so it's already done. Notice that these are small numbers. This one here, 0.0036. The D1, this is your knife edge reading across your first diameter. Then you rotate your mirror and you take a second set of knife edge readings, which is D2. Then you average them and you get D1, 2. Now here, column 9 is D12 plus or minus a constant, because we now have to focus the system. We have to focus it so our light is centered inside the airy disk. So I'm going to come to that in a minute, but this 10, this residual, is your knife edge position reading minus the constant minus your ideal, which is up here in column 4. So the difference between what you got and what you want becomes your residual, or your error. And that's what you're looking to see, that your error then calculates out by you take your error times this one here, which is your h over 4f, and you get your transverse aberration. Now the transverse aberration is going to be a small number. Notice this is 0.0018. You're multiplying by this, which is 0.0036. So that number is going to be 0.000000 something or other. So what you do is just multiply them all by 10,000 and bring the numbers up into a scale that we can really understand. They just become a 1 to 10 scale. And that's what the transverse aberration times 10 to the 5 means. It means that these are numbers that are times 10,000. The real number here is 0.000006. But that becomes a little cumbersome to think about. The next thing that he does is this is where he runs the test. He takes the transverse aberration and divides it by the airy disk diameter. This transverse aberration should always be smaller than the airy disk diameter, and if it is, then this ratio is going to be less than 1. So these numbers are going to be between +1 and -1. Any numbers that are greater than +1 or smaller than -1 are going to be outside the airy disk. And then this number here is just the slope information, where you've taken your transverse aberration and divided by the focal length to come up with your slopes. So you can run a graphical picture to come up with your wavefront analysis. So just a little bit about the constant and why you have to focus it. What you're focusing to do is to see that your transverse aberration divided by your airy disk, that your biggest positive number and your biggest negative number are essentially the same. And that what ends up happening, this is your biggest positive number and your biggest negative number. You've centered these rays but inside your airy disk, so that you've got the system focused. If the numbers are too positive, then you're on a high side here, you're not centered in your airy disk. If they're too negative, then you're focused long and they're not centered. So what you're trying to do by balancing with that constant is getting your light rays centered in the airy disk so you can run your airy disk analysis. So then all he does, this is the plot of transverse aberration divided by the airy disk. They're all going to be numbers less than 1, and you're just plotting it between +1 and -1. And what this shows is that all of the light from all your zones are clearly inside the airy disk. Good, you satisfied the Dijon encoder criteria of 1. This is a little bit harder to understand. You're looking for a wavefront analysis, and it's kind of a graphical sketch of the whole thing. Now let's just take away his working lines. This becomes the wavefront. This is just a scaled slope. He just drew this out 4 inches, the radius of his 8-inch mirror, and the first zone is 1.45 inches long. So you go 1 inch and then up 0.12, and then you draw a line at that slope till you hit the edge of your zone, and then the other one is -0.8, so you go out 1 inch, however far that is, and go down 0.89, and you draw a line that slope, and then you connect it with the next line here, which is -0.12, so it's a heel-to-toe graphical sum. And then once all this line is he's just showing that he drew a 4-inch line, and this is 0.12 times 4, so he could scale it and get that kind of slope. But you can, it's just a scaling thing. You can do it any way you want. And then after you're done, you draw in a reference optimum parabola here, and you look for your biggest gap between your reference wavefront and the wavefront that you just plotted. And this, you just measure this. In this case, it was 1.14 inches. And since this is scaled, it's a scale of 1 times 10 to the 6, your wavelength of light is 21.6 millionths, so it's going to be 21.6 inches long. So you take 1.4 divided by 21.6, and you come up with 1/19th of a wave. And that's how you get your wave rating. I know I went through that fast. I don't hope you get it, but I got a lot to say, and I don't have much time. But I'm hoping at least that little explanation, now you go back to your text row, and you'll be able to think it through, and you'll be able to get the idea of what he's trying to do here. Now, I have taken a 8-inch f6 mirror that I've tested and figured with autocollimation. You can see that the lines are parallel and straight, and when I do an autocollimation null, they're flat, a nice flat autocollimation null. The first thing you're going to do is look at the center of curvature and make sure the raunchy lines are smooth and parallel and so on. And you're going to look at your knife edge and you're going to null it out at the 70% zone. You're going to make sure you got a good edge and everything's smooth. And then I made up a table similar to his, except my 13 rows, I put 13 columns and then 4 rows for my zones and just did all the arithmetic. And the beauty of doing it in a spreadsheet is when I have this is my D1, my D2, and the average of the two, and then this one here is where I introduce the constant. I can just have this cell equal this cell plus the constant, which I can put up in some other cell, and then have all the arithmetic happen. And all I got to do to fill with that constant is just try a different constant in the cell, and all the numbers change automatically. And I can do that until my lambda f over rho balance, so I get, in this case, 0.188 and minus 0.188. I don't know how Texero did it in the old days doing it with a pencil, but doing it with an Excel spreadsheet is just magic. It just happens so fast and you can get the numbers. And then I can plot the transverse aberration. I could do his heel to toe arithmetic and come up with the scale off here of 0.8 of an inch, and wavelength is 21.6 inches, so it's a 25th of a wave according to this analysis. So this particular mirror meets both conditions of the Danjon and Coder criteria. And since I've done it on an Excel spreadsheet, at least the transverse aberration part, I can just simply plot that directly. Okay, now that we understand Texero, we can go the next step. This is the Mills-LaCroix method, Sky and Telescope, February '77. He took Texero one step further. Notice that Texero did not give you a boundary for your knife edge position. It gave you just put your knife edge into this analysis and we'll see if it meets the optical conditions. Mills and LaCroix said, I want to try to translate that back into a plus or minus boundary for my knife edge. And he did that with a very, very clever move. And in a subsequent article, A Telescope Making, number 33 by Robert Follett, his article called Efficient Mirror Testing, he spends part of that article talking about the Mills-LaCroix method and actually introduces some enhancements. And by creating just another couple of columns beyond what Mills and LaCroix did, you can make that transverse analysis plot and also that step-by-step toe-to-heel addition of the wavefront. Let's just step back and see what all Mills-LaCroix did was he took Texero's lambda f equals capital lambda c times h over f. We remember, first thing he said was, you know, we're doing all this at the center of curvature. All I need is a radius of curvature. I really don't need to deal with focal length. I know the radius of curvature is equal to twice the focal length. I'm going to make that substitution. So instead of 4f, I got 2r. Then I want to solve for this. And I want to solve for this error that I can measure with my knife edge. I want to solve for that at the limit where the transverse aberration is equal to the area disk. So I put rho for here, solve for this, and bam, I come down with the limit of my transverse aberration residual is going to be equal to times the radius of curvature times the area disk radius divided by the radius of my zone. When you do, you end up with a table that's much smaller than what you have to make up for Texero's method. And what you end up with is just radius. You come out with your zonal radii here. I got 4 of them for this particular mirror. This is my r squared over r, my ideal knife edge positions that I want. These are my measurements over here, which is really averages and columns that are beyond the scope of this chart. But this is the average. This one takes the measurement and adds the constant to it. And again, I have a spreadsheet so I can put that constant in some cell someplace and have each one of these point to that cell and do the arithmetic. I calculate over here the tolerance. This is my 2 times rho times r divided by my zone. So for each zone, it's going to be a little bit different. And then this becomes my ideal plus the tolerance and the ideal minus the tolerance. So these are my upper boundary, this is my lower boundary, this is the ideal of what I want, and this is what I got. And I plot those against the radius and I come up with a curve that looks something like this. This is my ideal r squared over r plot. These are my upper boundaries, my lower boundary of the knife edge position. Now in this case, I haven't really added the constant, so my measurements don't fit within the boundary. So I just fiddle with the constant until I get all my points the best fitting between the boundaries. So a couple of things here about the Mills-LaCroix curve. One of the things that you notice at first is it looks as though the tolerance gets a little loose towards the center. And it's not really quite true. What really is happening is that your knife edge has to move farther in order to reach the edge of the airy disc. You can see that a ray coming in from the edge of the mirror and just skimming the edge of the airy disc has a short distance to go, but a ray coming from the center part of the mirror just skimming the outside has a longer distance to go before it reaches the limit. And that's really what this horning out actually means. The other thing that you ought to keep in mind when you're using the Mills-LaCroix method is that the scale is pretty dominated by the r squared over r function. With an 8-inch f6, you still have a reasonable amount of width here, so you can tell if your measured points are within the boundary. But if you get to something like a large diameter and a fast focal ratio, then the scale of your curve just becomes so dominated by your r squared over r function that you just can't even separate out your boundaries and tell whether your measured points are within that. So another way to display this is to factor out the r squared over r. And when you do, you end up with a much simpler thing. You've got your zones, and all you've got is your residual error. You haven't added it to or subtracted it from your r squared over r. And then all you've got is your plus boundary and your minus boundary. And you end up that your ideal would be a straight line, and you got your upper boundary and your minus boundary, and you've got a lot more range in here, so you can see how you get a lot more resolution on your points. This is the 8-inch f6 mirror. The resolution that would show up on the 6-inch f4 is just about the same. You get a much nicer, much clearer picture of what's going on. Also, if you read Ken Follett's article, and I just don't have the time to really, I wish I had the time to just spend just a little bit about the 2 or 3 columns that he introduced, but they're really fairly simple, and it enables you to directly plot from the readings taken and the other Mills-LaCroix information. You make the same plot of transverse aberration, so you know this is your +1 and -1, which is your airy disk size, so you know that all your light is clearly within the airy disk, and it actually does for you finding these points, this heel to toe addition to find your wavefront. So you can plot that directly in your Excel spreadsheet, and then you could draw in your reference parabola and make your scale measurement, and actually in this case it's just a subtraction of this number to this number to find out your wave rating. But the clever thing is, because it's on an Excel spreadsheet, you can just tweak your constant a little bit. There's some argument as to whether this is legitimate treatment. It would be better if these 2 points were on a straight line here, and you can just tweak your constant so that they are, and then you can just read directly your wavefront error and calculate it. In this case, it's a 20th of a wave. So do I believe that this is really a 20th of a wave mirror? Absolutely not on your life. I just want to point out that we have an inherent error here, just an inherent problem in all of this knife edge measurement thing. We're trying to measure an x against a y. The x-axis or the y-axis this way is your zonal measurement. Your x-axis is your stage with your knife edge. You can make a very precise stage, and you can put micrometers on it. You can put ball bearings on it. You can measure the position of that knife edge to a 10,000th of an inch. But you cannot define your shadow to that same level of precision. It's like trying to measure a napkin with a vernier. You just can't do it. I remember the phrase when I was in the service, measure it with a micrometer, mark it with chalk, and cut it with an axe. Well, that's really what you're trying to do here. Really, about the best level of precision that experienced people can get is to get a knife edge reading to repeat within about 10,000ths on your knife edge reading. So notice your boundary here on your Mills-LaCroix curve. Notice where your plus and minus 10,000ths are. So you've really got kind of a range in here where your data points are probably going to be within your ability to be able to read them. Now I took those points I had before, and this one here I adjusted by 1,000th, and this one here by about a couple of thousandths and a half, this one by half a thousandth, and this one by about 8,000ths to come up with this kind of a characteristic. And when I do and run it through, I get a 16th of a wave instead of a 20th of a wave. So just a few thousandths change in your knife edge reading is going to give you a lot of change when you're dealing up in these lower numbers. I don't really care if it's a 20th of a wave or a 16th of a wave. Point is, it's better than a 10th. And that's what you need to go home with, is that it's better than a 10th. It's as good as a mirror needs to be. It's as good as I care to have it. I'm not out there to brag that I got a 20th of a wave mirror. I want one that's in a telescope that I can look at the sky with. Just to show you how good the Mills-LaCroix boundaries are, if you actually take some points, and Robert Follett did this in his article, and just scatter the points widely, you'll find that you're still within the airy disk and your transverse aberration. Your wavefront comes in to be about a 1/5 of a wave here. So staying within this airy disk on this de Jonge encoder criteria really gives you a pretty darn good mirror. Now I thought just one last parting shot here. Remember I told you that this original method, this classical method, gives you a boundary like this for your knife edge. And what I did was just let you know that this does work. I plotted the undercorrected boundary in the Mills-LaCroix and the overcorrected boundary in the Mills-LaCroix, and both of them fit within the Mills-LaCroix. So those boundaries are good boundaries, even though they're not totally backed up by science. So really, that's about all I have time for. In fact, you're probably fallen asleep at this point and bored of listening to me. But I hope that I've given you some value. I hope I put in a little bit of perspective. I want you to make mirrors. I don't want you down there spending 3 years trying to tweak some mirror into a 25th of a wave. It's just not there for you if you do. Unless you're into some kind of bragging rights or something. Once you get beyond a 10th of a wave, you're there. This is 10th of a wave, peak to valley, at the wavefront. There are other ways of expressing wavefront. It's a surface wavefront, plus or minus your nominal. Unfortunately, I just don't have time to go into that right now. So, thank you very much.